I'm Peter Laval. Hello. Thank you for joining me. I'm going to go through my workflow for what I'm calling a domain-specific language for interface description within a cross-paradigm programming context. It should go without saying that I'm going to ignore a lot of the details of everything that I've written for my PhD. Overviewing the entirety of the monstrosity I've put together for my PhD is not necessarily an effective use of anyone's time. What is interesting, what I thought was amusing, was that I've found a way to embed the relatively intricate control structures needed to interact with functional reactive programming into a much more crude and simple object-oriented programming language in a way that lets me quickly change them and adjust the types of them, or adjust the type signatures, or add arrays of data. This has become a very flexible solution because the model, the meat of it, is specified in an interface definition language file, which is then used to generate the more elaborate boilerplate constructs to pack and unpack the data as it crosses the barriers between Scala and PureScript. With that in mind, I'm going to run through the steps that I would take to produce this system. Following that, I'm going to briefly talk about what I've got as a result. I'll try to address some of the concerns about what is or isn't good about this, but I'm relying on audience questions throughout this presentation, even though it's pre-recorded. Finally, I'll do the rattling off of a few interesting ideas that I say I just need a few more hours in the day for. So there are two workflows in question here. I'm going to walk through the full bootstrap workflow to get the initial iteration of the system working. I've used this for several hobby systems, so it came quickly to mind when I needed to do this for my PhD. Once the initial bootstrap workflow has been related, I will detail the Chicken Little approach to adding more functionality, or expanding or otherwise correcting existing functionality. So even without actual tools, I still think it's a good idea to start with an interface definition language. Even if you can't formally use it or compile it or run it, even if it's just something that you look at and you have in your documentation or in your paper notebook, it's neat to have your idea written down so it can't twist and writhe in your mind while you're working. In my real project, this is the interface definition language file for the Mary's text-to-speech system that I'm using. It specifies which data can go between Scala and PureScript using what looks like a pseudocode format. Now, you can sort of look at this already and almost see exactly what can be done between these two systems if I explain that the functions, members, methods marked with exclamation parts go from PureScript to Scala to indicate how this foreign signal function should be acting, whereas the methods marked with question marks come from Scala into PureScript to notify the functional reactive network of changes. So an ideal result of this approach is that a human can somewhat quickly understand what the pile of source code is doing. If you're building a system from scratch, it probably makes a heck of a lot more sense to start with something more hello world like this. this has what I call a pipe type of signal function. This pipe signal function can be set to ignore or listen. And this pipe type of signal function can send in an event to the network that it has heard some text. The implication here is that this is a speech-to-text system. This speech-to-text system can be muted or deafened, and this speech-to-text system will send input into our functional reactive network, triggering the network to recalculate and reconfigure itself, as well as providing new signals to output to the Scala code saying how the components should act. Should they now become mute? Should they now be listening? In any case, the code that is generated from this is not something that stands alone. Both the PureScript and the Scala and even the JavaScript that's generated are really dependent on the outer constructs, the other constructs that exist. This is not a Turing-complete language. The constructs generated will never do anything useful on their own, and that is fine. What they will do depends on the context of what you're doing with this. More simply put, to progress, we need to follow a use before reuse approach where we look at the specification and then we implement the rest of the system this specification would indicate exists, and probably also a demo that uses the functionality that the specification would expose. At some point, I ended up creating PureScript like this, which is very similar to the specification, but already longer and less clear. There's also implementation details. This function on the bottom, the implementation would be generated. Most likely it would work by invoking 3 different foreign functions. One foreign function opens the thing, another foreign function sends a signal, the S, out. A third foreign function checks for an event E. This is not an insubstantial amount of functionality, but once this functionality is tested and known to work, and your structure, your conventions are sort of stable, the next step is to create the actual code generation. So to do that, you need a sort of intermediate model or intermediate representation, or even you could call it a domain-specific language that represents that first file, which looks like this, in a more traditional programming language that looks like this. To be proper good, you should parse the original file into that tree on the bottom. With that tree in mind, you then want to go back and emit source code for the module we saw earlier, a PureScript. You have this tree on the bottom already, and you want to create a chunk of text. So you use a text template engine, which might look something like this. There will be more details in the real world, but you can already see opening the handle and passing the signal and event out differently. There are many more details to this than I'm letting on. They're tedious, they're dull. If you want to see the full example of this actually in action, I have a GitHub repository with the real system, but it's large. It gets large. In a cathartic penultimate step, you connect JUnit to parse your interface definition language files, generate and check those models of what the file says before constructing the final generated source code. This is all done as a series of comparisons. For the text comparisons, I like to take the step of normalizing the text, removing comments and white space, altering indentation to be automatically consistent, fixing new lines and carriage returns, and if the normalized texts differ, I will dump both the original texts, 2 files on disk, and raise an error message which includes a kdiff command line that you can then run normally by hand to get a good comparison between the 2 files. This isn't a crazy innovation, but it does speed up my edit, compile, test loop enough that I think it's worth mentioning. Finally, with those tests passing, you have programmed the computer to generate the identical source code to what you already wrote. So you should hook up some step of your build process to rerun this generation whenever the project is compiled. How you do this depends on what build tool you're using. In my case, I'm building my Scala code with the SBT Build tool. As such, the SBT file looks like this. I'd like to mention that I don't expect this to make a lot of sense to the audience. I just want to be clear, I'm actually doing this, and my build generates source code that it then adds to the list of things to build and compiles. So with one of these running and one of these working, you can add many components just like this with only these primitives. More likely, you're going to need more functionality than already shown. To add additional functionality, you should modify the interface definition language, adding new constructs. By new functionality, I mean things like new variable types or parameters. Maybe you don't want to pass everything in and out as a string. Or maybe, when you hear spoken words, you want to know how long they lasted. So here, we've added a second parameter to the heard event. As well as text, you get a double precision value of how long it took the human to say whatever has been recognized. You might have noticed a typo. When doing this, you want to retain your original unit tests as a sort of regression. You would copy and paste the simplest test that's close to what you want. You would then update that old test to do the new thing, which will lead to compile errors, probably. So you'll expand your intermediate representation, your model, your abstract syntax tree, whatever. You would modify your parser to handle the new concepts, any new concepts. And you would update your templates with any changes you want reflected in all of the regenerated source code before regenerating your source code. At this point, you'll be able to rerun your system with the changes and see whether or not it worked perfectly. You might end up wanting to disable source code regeneration while doing this, in that you might add this new functionality, generate the source code from the new functionality, and have a tiny little change you want to do to it. Maybe there's a typo. Maybe there's an extra comma. Disabling source code generation, editing the generated source code until it works right, then going across to the unit tests, fixing the expected outputs, then fixing the templates, and then possibly fixing the parser as needed, is a perfectly acceptable workflow. As you add more functionality, I would advocate adding it to teeny tiny files, to hello world size examples, each of which demonstrates one aspect of the system's functionality. This is instead of creating a zoo test that tests everything at once with all the features. Having it in small little files helps you zero in exactly what breaks when or if something breaks and generates unexpected or different source code So yeah, we now have a simple approach to generate lots of boilerplate source code for defining interfaces between different components that don't necessarily act in the same way. This can replace some relatively intricate language constructs if we hook it into the build process correctly. Not too shabby. I've also added some stuff for generating random streams of inputs. My generated stuff uses a lot of inheritance. Even though it's all generated and could do everything inline, it seems more wise to inherit from some base classes that aren't generated and exist prior to running this build tool because they were written by hand. A simplified view of the generated Scala looks like this. If this had been handwritten, the first two case classes would have been case objects. The third case class shows that this can take a string. So this generated Scala doesn't include the double shown above. The trait shown at the bottom is extended by whatever wants to create a new world listener. When that thing is invoked, it's expected to produce a factory that takes a way to send an event in and returns a closable item that can receive signals. Again, the real implementation, which is on GitHub, is considerably more verbose. It's generally going to be up to the component author to implement that trait, put it in the right place, and then put their implementation in the right place so that the whole thing meshes together as intended. So why not just use inheritance, generics, monads, reflection, macros, or other pre-existing language features? There's no general reason why the approach I'm describing today should or even could replace all these things. I don't think that this is the best approach for every situation. This approach would be an absolutely terrible solution in any case where a built-in language feature was available. I did start this project with a monadic approach. I found using a monadic approach, I had to invoke all my function primitives in order to work out what their types were, which meant that I couldn't generate the code until the system had started. In addition, relying on runtime reflection is always a disaster waiting to happen, in my mind, as inevitably any JVM code somebody will try to push through a bytecode obfuscator or run on the Android virtual machine. And by someone, I mean me. Runtime reflection in the Java virtual machine is not something I'd call reliable or fire and forget. I'm not using Scala macros, and I think that's kind of potentially a failure on my part. I wasn't able to grok any version of the macro instruction manual beyond the basic hello world macros that they all explain. The approach that I'm using does have more control than the macros, as again the Scala code I'm writing doesn't have to run other than the Scala code, which happens to be the source code generator. It's nice to think that the PureScript generation is decoupled from running the actual Scala project. In reality, the biggest obstacle, the biggest cost of this is the time involved in spinning up the first iteration of this. It also does sort of commit you to working in a certain way, and any modifications or changes that need to push through sort of require validation and testing. Thanks for listening this far. I want to keep working on this as and when I have time. There are a few language features I'd like to add, and things I'd like to remove, and aspects of how it works I'd like to change. The obvious sort of one is that the sealed traits presented above for events and signals almost look like Scala 3's enum data types, which are basically equivalent to the Haskell and PureScript data types. An obvious feature that I don't want to include is the ability to add inline source code to the interface definition language files. I think that the interface definition language files should only define the interface rather than implement it, or rather they should only describe the interface rather than develop it. I think that their brevity is a feature in that you can look at them and read them and you don't care how they work. You just sort of know what they're doing. Encoding data to buffers and streams looks a lot like the protocol buffers that this was mirrored off of. It would be nice to be able to do that as a way to save and restore sessions to allow regression testing of interactive agents. A really interesting idea I keep having is to emit enough support gunk that one can create a Python component which runs in a completely separate subprocess by only specifying a very basic script and a list of pip packages that the Python component should install. This would be a great approach to get around the Python global interpreter lock and gain access to the functionality and packages that have already been prepared and are available within the Python ecosystem. Torch, TensorFlow, and Pocket Sphinx are three of the obvious ones. The final crazy idea would be to generate C++ code and build C++ base interfaces, and in general build a C++ version of the running agent shell. This isn't actually hard, it's just slow. This wouldn't require forgoing the existing Scala management to launch everything, but it really isn't within the scope of useful work for this PhD. So that's it. Get in touch if there are any more questions.